Hello students, I am Dr. Gajendra Purohit and you're watching our YouTube channel where I share videos on engineering, mathematics and B.Sc. If you're studying for any competitive exam that involves higher mathematics, then our YouTube channel will be helpful for you. In this series, I've launched Fourier Transform 2.0 series, where I've discussed various questions related to the topic. Today, I'll be covering some problems based on the Fourier Cosine transform. In this topic, we have some questions that involve proofs. For those, you'll need to apply the inverse Fourier Cosine transform. So, let's get started. Let's see what the formula for the Fourier cosine transform is. Typically for any function fx, its Fourier cosine transform is given by root 2 by pi 0 to infinity fx cos sx dx, and for the inverse the fx will move out and fs will take its place, right? In other words, fx is replaced by this fs and then the integration will be with respect to s. That results in the inverse Fourier transform, but students wonder about the derivation, so the concept is the Fourier transform is as such. If we are given any function and if we need to find the Fourier transform of that particular function, so we have the Fourier transform here as 1 upon root 2 pi from minus infinity to infinity e to the power iota sx fx dx, and we know that this value is expressed in terms of s. Now if we open up this formula, it will be from minus infinity to infinity e raised to the power iota sx. We write it as cos sx plus iota, and here we are getting fx dx included in this expression. If here we separate the real part and the imaginary part, so this will be from minus infinity to infinity fx cos sx dx and plus iota 1 upon root 2 pi minus infinity to infinity, and we will get fx sin sx dx. So this is what we get here. This means that we have represented this function separately in terms of its real and imaginary parts. And suppose if we are given an fx here, and if it is an even function, then in that case we will get its value and here it will be 0, right? If we work through this, then we see that it extends from minus infinity to infinity. So this will become 0 to infinity into 2, and from here we will get the value as fx cos sx dx, and this will become 0 because we have an odd function. And if fx is even, so even multiplied by odd becomes odd, right? Moving further, we will cancel this with 2. So this will come out to be 2 by pi, the integral from 0 to infinity of fx cos sx dx. And this formula that you see is called Fourier cosine transform. And in the same way, if the function fx is an odd function, then in that case it will become 0 because an odd multiplied by an even number is odd. And here we will be getting this odd multiplied by odd as even. So in that case its value will be 2 upon root 2 pi from 0 to infinity fx, and further we will get sin of sx dx, and we will simplify this, then we will be getting 2 by pi from 0 to infinity fx sin sx dx. So this is something that I will explain in the next lecture, including how to find the Fourier sine transform and the inverse Fourier sine transform. I will cover that later. For now, I am explaining the concept of the cosine transform. If you forget it, you can easily derive the formula from the Fourier transform. Here you should consider fx as even. This is just a derivation. If you happen to forget this formula during the exam, there is a way to remember it. I will briefly review it for you. If we have a function fx and we need to find its Fourier cosine transform, we will write fc here. Fx, and here we will be getting 2 divided by pi from 0 to infinity fx, and here we will be getting this cos sx dx. Ultimately, we denote this as fs because the result is expressed in terms of s. Alternatively, we might refer to this as fcs as well. So what we have here is the value of the Fourier cosine transform, right? If we use the inverse Fourier cosine transform, which we represent as IFCT, then we can write this as the Fourier cosine transform, which we can write as FCT for short. In that case, we will get FC for the Fourier cosine transform and FS for the Fourier sine transform. So here we will be getting 2 by pi from 0 to infinity, and this will be fs cos sx and dx, and the form in which it is presented to us actually appears as fx. Ultimately, if we need to find the Fourier cosine transform of any function, we obtain this value and its inverse returns the original value. So we can easily find the inverse this way. So if asked about cosine, we will use the cosine transform. Sometimes we may need to use both cosine and sine transforms. So you should know that we will represent cosine with the letter C here, and for sine we will use S to indicate it. Sometimes some books may not include all the details that you need to fully understand a concept. In that case, it's essential to pay close attention to the specific question being asked. Some books will be providing just this 0 to infinity and here 2 by pi written. So don't worry, when you need the inverse, just take the value of fs and substitute it here. You'll get root 2 pi into root 2 pi as 2 by pi. So ultimately, these formulas are also used in some books. The Fourier cosine transform is this, and the inverse Fourier cosine transform is 2 by pi 0 to infinity fs cos sx dx, right? There's no need to worry about it. Now let's try to understand how questions typically appear in exams. The question states find the Fourier cosine transform. So this is the function given. Now I will directly write FCS here, right? I am taking the Fourier cosine, and the formula we use for this is 2 by pi. The integral runs from 0 to infinity and it will be fx multiplied by cos sx and dx. This will be represented as 2 by pi. Now we need to examine the interval form, so we write it separately here. So in the 0 to 1 part we have x. Now first we write it as 0 to 1, fx cos sx dx. Then I will write 1 to 2 here and we will get fx cos sx dx. Then we will get from 2 to infinity fx cos sx dx. Here I have taken the 2 by pi outside, making it common. Is it understood? Now here you need to pay attention. It will be 2 by pi. And here we will be making 0 to 1. The value of fx would be replaced as x. So between 0 and 1, its value is x. Then we will get x cos sx dx. Plus the value of this is 2 minus x when going from 1 to 2. And cos sx dx. And from here, this is coming out to be 0. So the entire value will be 0. Now what we need to do is integrate it by using the IIT method. So students, here we get 2 divided by pi. If you are familiar with using the IIT method for integrating, you should know how to proceed. So we'll set aside x. We will integrate cos sx minus the differentiation of what was left aside here. And again here we will be getting cos sx and then dx and the dx of the total this way. And the limit will be 0 to 1. Similarly, we will proceed to do the same here, right? I am writing directly from here. We will leave 2 minus x, and if we do the cosine, then it will become sine sx upon s. See, the derivative of minus will be minus 1. Note that if you differentiate twice, once it will be here and then again it will be there, so the derivative of cos is sine. The sine will turn into negative cosine. So with the minus sign occurring 3 times, so this minus will remain. So here this will result in cos sx divided by s square. The limits will be from 1 to 2, giving us this value here. If you notice here, I haven't carried out the integration myself, but it's been completed here for the purpose of demonstrating how we use IIT, right? Now we are getting x. If we take the cos, we will get sine sx upon s minus 1. And if we apply cos once, it turns into sine. If we take the sine, it will be negative and the cos will be positive. And this will be cos sx upon s square limit. From 0 to 1, let's write as it is. I will apply the limit later. Here we have plus and then 2 minus x. Sine. The expression will be sx upon s minus cos sx upon s square, and the limit will be from 1 to 2, right? Let's continue. So it will be 2 by pi, and here we'll apply the limit. Wherever x appears, we will substitute 1. So we will get sine s upon s, and at this place it will be cos s upon s square. Since the second limit is 0, so by putting 0, it becomes 0. Since sine of 0 is 0 and cosine of 0 is 1, right? So this will give us this value. Plus, this will provide us with the result. Clear? Plus, if we place the limit here, then 2 minus 2 will be 0, right? And placing 2 here, we will be getting cos 2s divided by s square minus, and putting 1 here. It will be 2 minus 1, which is 1. So this will give us sine s upon s, and putting 1 here. So this becomes plus cos s upon s square, right? So this way we get the value. Now you will notice that some terms will be cancelled out here. So some terms are getting cancelled here. Look, this term and this term are getting cancelled here, right? So the rest of the value is 2 by pi. If you notice here, we have cos s upon s square and here cos s upon s square plus. So I will write it 2. Cos s upon s square. Now the value we get is cos 2s upon s square minus 1 upon s square. Let us simplify it a bit. So here we will take the LCM of s square. And the value of it will be 2 by pi. And here we will be getting it as 2 cos s minus cos 2s minus 1 upon s square. So the value of its Fourier cosine transform is this. Thus we can solve it very easily this way. As you can see the solution here. In this solution here, you can notice that we had cos 2s and then we substituted the value of cos 2s in the formula, which is 2 cos square s minus 1. And this 1 will cancel out with 1. So this will be our answer. Clear? Let's move ahead now. If you are preparing for the CSIR NET, GATE or IIT-JAM exams, you can purchase our books on Amazon. They are also available on Flipkart. The next question is very interesting. It says, find the Fourier cosine transform of fx is equal to e to the power minus x, and you have to prove it as well. Whether it's a cosine, sine or a standard Fourier transform, you must use the inverse when proving something. In the case of this cosine question here you will have to use the inverse Fourier cosine transform as well. Let's see how do we do this. We have a function fx, and if we want to find the Fourier cosine transform, so we know fs is equal to 2 by pi, and here we have 0 to infinity, and from here in the equation we will be getting this fx cos sx dx. So the value we will be getting here is from 0 to infinity of e to the power minus ax cos sx dx. This is the formula if you have studied this. So here we have a formula where e to the power ax cos bx dx, and then its formula is e raised to the power ax a square plus b square a cos bx plus b sin bx, right? So we are going to use this formula here. As you can see, we will have its value as e to the power of minus ax, a square plus s square minus a plus, and here we will be getting cos sx plus s sin sx. And here the limit we are considering will be from 0 to infinity. When we apply the limit, it will be 2 by pi, because e to the power of minus infinity will be 0, so it makes the whole term 0. If you place it here, then this will be a square plus s square. The value of cos 0 is 1 and sin 0 is 0, so it becomes minus a. We will simplify this and we get 2 divided by pi. Here we will get a upon a square plus s square. So this will be the Fourier cosine transform. Clear? So we need to prove this, and for this we need to use the inverse Fourier cosine transform. Let's see. Now we will use the inverse Fourier cosine transform. Okay, in order to prove this, in this inverse Fourier cosine transform, this fx is taken out, right? And this fs will go inside, then this will be 2 divided by pi. 2 by pi, and it will be from 0 to infinity. This will be fs. This will be cos sx and ds. This is what you need to pay attention to. Now the fs we calculated, if I take its inverse, its value should be e raised to the power minus ax. If you get e to the power of minus ax, then its inverse will be e to the power of minus ax. Keep this in mind. So replace this fx with e to the power minus ax, and this will be 2 upon pi from 0 to infinity. Here the value we are getting is 2 divided by pi and a upon a square plus s square, and this will be cos sx and dx. So take this out and I'll write it over here, okay? This will be 2 by pi from 0 to infinity, right? 2 by pi from 0 to infinity, a upon a square plus s square cos sx ds will be equal to e to the power minus ax. Now, as you can notice here that wherever you need to prove, you will have to replace x. And for that, we will require m. We will put x is equal to m, and after considering this will be 2 by pi from 0 to infinity a upon a square plus s square cos sm. ds is equal to e to the power of minus am. As we know, it has the finite integrals property. If we have s ds here and I replace it with x, it won't make any difference. So I simply put, if s is equal to x, then ds will be equal to dx. We need to replace s with x here, so we will substitute it. The limits are 0 to infinity. This will be a upon a square plus x square, and this will be cos xm dx, and if we take it over there. So this will be pi by 2 and e raised to the power of minus am. Using this method, you can easily prove it here. Sometimes you are given pi by 2a, then in that case, you just have to take this a outside and bring it to the denominator, right? So you can take out this a, and in this way, such a question will also be easily proved. Clear? Let's continue. Such questions are asked in exams. Find the Fourier cosine transform of fx equals to 1 upon 1 plus x square. Now we need to know the formula. And the formula we have is fs is equal to 2 upon pi from 0 to infinity. This will be fx, and cos sx dx is given. We will put the value of fx here, and then we will consider it to be I. So I have taken fx as I. So 2 by pi. And this will be from 0 to infinity. 1 upon 1 plus x square cos sx dx. Since the integration is difficult to calculate, I will differentiate both sides with respect to s. Now in the process, we will do di by ds. As you can see, s is only here, so we will find its derivative by using Leibniz theorem. As we know, it will be from 0 to infinity. So here, when you differentiate it with respect to s, then you will get 1 upon 1 plus x square, and the cos becomes sin sx. Here x will come forward, and because the derivative of cos is negative, this will be negative. So according to the Leibniz theorem, if you have d by dt of a to b, we have been given fx dx. So in this process here, the derivative goes inside d by dt of the integral from a to b of fx dx. Next, wherever there is an x, we substitute with the upper limit. So we replace x with the upper limit and then we perform the derivation of that upper limit. Then we subtract the lower limit here and then we have the derivative of the lower limit, right? Since both the upper limit and lower limit are constants, they will both be 0. Here, we will find the derivative of the function we have in fx with respect to t. Since we have s here and s is also present here, thus the derivative of this will be sine sx and x will come out in this equation, right? This concept is about the Leibniz theorem. If you are not familiar with this topic, then you can watch my YouTube videos on it or find its video on IIT-JAM. Clear? So here it will be d by d. Sorry, I wrote it wrong. So students, this will be di by ds is equal to minus 2 by pi from 0 to infinity of x upon 1 plus x square. X upon 1 plus x square. Now you need to pay attention here as we are using a trick to solve it. So the trick is, to integrate this, we will multiply it by x in the numerator and the denominator. So it will be x square. Then in the next step, we will add 1 and subtract 1, right? If we do this, this question will become a little easier for us, right? So let's solve it further. di by ds is equal to minus 2 divided by pi. It is from 0 to infinity and we write 1 plus x square below it. So this will be 1 plus x square upon x, 1 plus x square minus, and here we get 1 upon x into 1 plus x square and sine sx dx. So here I will put the bracket on this expression, right? As you can observe, we have a few terms including this 1 plus x square and they got cancelled. Now I will simplify this. So it will be di by ds is equal to minus 2 by pi. This will be from 0 to infinity. So we are left with 1 upon x and this will multiply inside. So this will become sine sx upon x. Dx will become negative. So students, it will be from 0 to infinity. Here we will get the value as x, 1 plus x square. It will be sine sx dx. If you want, you can multiply 2 by pi inside the integral. Then the minus and minus will become plus. And further, it is 2 by pi. As this minus will shift here, we will get the value. So we have a result here. If you've studied Laplace and Fourier transforms, you know it ranges from 0 to infinity, right? We are given here this expression sine x upon x dx. The value of this integral is pi by 2. We can easily prove this using the division property of the Laplace transform. If you haven't seen it, you can see the Laplace division property by referring to the IIT-JAM. We have the result of this and we will use it here. This will be di by ds. We even explained this in Fourier transform. If you've seen my first video on it, then I also proved this there. You can also watch and learn it from there. Now the value we will get is 2 by pi, right? And as you can see, the value of this particular expression that we have will be pi by 2. We will take it as pi by 2. The rest will remain as it is. So we will write this as it is. This will be 2 divided by pi from 0 to infinity. And this will be 1 upon x, 1 plus x square. And students, here we will get the integral of sine sx dx, right? Now we will differentiate this again. So when I differentiate this again, it will be d2 by I. I will again take the derivative with respect to s, and since this is a constant, it becomes 0. So pay attention. This will be 2 divided by pi. And from 0 to infinity, the derivative will be with respect to s. So the sign will become cos and x will come in front. As you take x forward, this will be x. 1 plus x square and this will become cos sx dx. So this x will cancel out with this x. And the value of this will be equal to I. So I will put this term as equal to I. So we will get d2I by ds square is equal to I. Now we will simplify this and in the process we will get a differential equation of this type. We already know that we will need to formulate the auxiliary equation right here. So the value of m will come out to be either positive or negative 1. So if you take a closer look here, after solving this question, we will obtain the value of I. That will be c1 e to the power s plus c2 e to the power minus s. And here we write I at s is equal to 0. So here we have c1 plus c2. Next, I will differentiate this, right? I will calculate di by ds. When we differentiate this, this will be c1 e to the power s minus c2 e to the power minus s, right? Now we do di by ds. Let's set s is equal to 0. So this will become c1 minus c2, right? So these are the two results that we will be using here. Now the question we had about I was this. So in the next step, we will be considering this I here. We write I at s is equal to 0. We will substitute s with 0 in the equation for I. We know that cos 0 will become 1. Therefore, the value will be 2 by pi. From 0 to infinity of 1 upon 1 plus x square dx. This cos 0 will be 1. If we substitute this value, then this will become 2 by pi. The value will be tan inverse of x and the limit will be from 0 to infinity. So, in this, when we substitute infinity, we get tan inverse infinity, which is pi by 2. If we substitute 0 here, the value will be 0. Upon simplifying, we are left with the square root of pi by 2 after cancelling out the 2's. When I at s is equal to 0, we get its value. Here we have I at s equals 0. If we combine these two, so with these same results, at I at s is equal to 0. Combining both these results, we will get C1 plus C2 is equal to root pi by 2. We will have this equation that will be formed. Now wherever we have di by ds, we put s equals to 0. So di by ds is this. We calculated di by ds and replaced s with 0, so sin 0 is 0. And if we notice it here, then this di by ds at s is equal to 0. If we put it here, this entire expression will be 0 and the value will be this. So if we simplify this, then the value we get is minus pi by 2. Right? So here, as you can notice, we have di by ds. Here, the di by ds is this. So we have the second equation, which will be C1 minus C2 equals minus the root of pi by 2. Now, our next step in this process will be adding them. We add them, right? When I add both of them, C2 cancel out each other and so do they. So the value of C1 will be 0. So students, the value of C2 will be root pi by 2. And as we know that C1 is 0 and the value of C2 is here, we will take these two values and put them in this result. So we get the value of I because here we need to find the value of I. So we have this I. We need to solve for it. So the value of I will come here. Now we will put the value of C1 as 0 here and the value of C2 here. The answer we get will be root pi by 2. E to the power of minus s will be the answer. And if we solve this, the value of fs will be pi by 2 into e to the power of minus s. So in this way, we can easily do this here. I believe it is clear to you. Please let me know in the comment box about the time it took you to solve this question. Please do comment and let me know if you want to watch more videos on Fourier Transform that I uploaded 4 years ago. You can find the entire series here and my 2.0 series is also available here. Check it out and also do subscribe to the channel. Thank you. Bye.